Hi there, and welcome to the Science Lullaby. I'm really glad you're here. As you settle into a comfortable position, whether you are resting in bed, lying on your side with the room dim, or simply sitting quietly with your thoughts unwinding, let yourself soften into this moment. Your breathing can slow, your body can loosen its grip on the day, and the noise of everything you've carried can gently fade into the background. Tonight, we're going to enter a space where calm and curiosity move together, where the mysteries of the universe unfold slowly enough for your mind to relax into them. Somewhere inside you, maybe deep beneath the surface of everyday worries, there is a part that still wonders about existence with the same openness you had as a child. A part that looks at the sky and feels that tug of possibility. A part that senses there must be more to reality than what we experience in a single lifetime. And tonight, we're going to follow that feeling into one of the most intriguing questions modern science has ever touched. The question of whether there might be other universes, other timelines, other versions of events, and perhaps somewhere in those possibilities, another version of you. For thousands of years, human beings have asked what lies beyond the visible world. Every ancient culture had its own way of expressing this mystery, from parallel realms in mythology to layered heavens, spirit worlds, and cosmic cycles. Back then, these ideas lived in stories and rituals. But as science grew, as our understanding of space and matter deepened, something remarkable happened. The old intuition that reality might be far bigger and far stranger than it seems found new life in physics, mathematics, and cosmology. Tonight, you don't have to struggle to grasp every detail. You don't need to analyze or memorize anything. Just let the ideas move through you. Let them drift the way deep ocean currents drift beneath the surface, silently shaping vast expanses of water. As you relax, you can allow your awareness to float gently, without effort, through the concepts we'll explore. The possibility of parallel universes arises not from imagination, but from the limits of what we can explain with the laws of physics. Quantum mechanics shows us that particles do not exist as fixed objects, but as clouds of possibility, capable of multiple outcomes at once. Cosmology tells us that the early universe may have expanded in such a way that countless regions grew into separate, self-contained realities. The mathematics of higher dimensional theories suggests that our universe might be just one surface among many, all coexisting in a deeper structure of space and time. As you listen, allow yourself to sink into this enormous scale. Let the smallness of everyday troubles fall away for a moment, replaced by the quiet feeling of drifting through something vast. This journey will carry us through ancient history and modern physics, through the strange logic of quantum experiments and the dizzying implications of cosmic inflation, through philosophical questions about identity and consciousness, and finally toward a deeper reflection on what it means to exist at all. So breathe gently and let your thoughts become lighter. You can let go of the day. You can rest here. Whether you drift towards sleep or simply drift into a calmer state, your mind is free to wander. Tonight, we step softly into the question of parallel universes and into the possibility that reality might be far richer, wider, and more mysterious than we ever imagined. For as long as people have been able to think about their own existence, they have wondered how different life might have been if they had made other choices. Even in ancient times, humans sensed that their lives could have unfolded in countless alternative ways. A moment of hesitation, a conversation that never happened, a road not taken. These small points in time have always made us wonder whether there could be other paths, other outcomes, or other versions of ourselves living out those possibilities somewhere else. The idea feels emotional, personal, and deeply human. Yet modern science has elevated this simple question into something far larger. What if these alternate versions are not just metaphors or daydreams, but actual realities that coexist with our own? Before we even consider the physics, it helps to understand why this question matters. Every person carries a private universe inside their mind, a world made of memories, habits, fears, desires, and choices. Each choice closes some doors and opens others, shaping the trajectory of a life. When we think about another version of ourselves, we are really thinking about the fragile structure of identity. We are asking what makes us who we are, and whether our uniqueness is absolute or merely one possibility among many. This question has always been at the heart of human introspection, long before we had language to describe quantum states or cosmic expansion. But in the last century, something unexpected happened. As scientists examined the building blocks of reality, they found that particles do not behave as single, definite objects. Instead, they follow mathematical rules that allow them to exist in multiple states simultaneously. This behavior is not philosophical speculation. It's been demonstrated repeatedly in experiments. The smallest components of the universe seem to hold many possible outcomes at once, only appearing to choose one when measured or observed. This raised an unsettling possibility. If reality itself contains multiple outcomes, then the version we experience might be just one branch out of many. This is where the question of another you becomes more than imagination. If the underlying laws of nature generate multiple possibilities at every moment, then the chain of events leading to your existence might also contain countless branches. In one branch, you are listening to this right now. In another, you might be somewhere else, living a slightly different life, shaped by one or two choices that diverged long ago. The versions of you in those branches would not be fictional characters. They would be real, physical consequences of the same natural laws we observe every day. Some scientists resist thinking about the idea in personal terms because it seems to blur the line between physics and philosophy. But science is not separate from human experience. Our sense of self is built from physical processes in the brain, and the brain is built from the same quantum particles and cosmic materials that fill the universe. So when we ask whether another version of you might exist, we are not stepping out science. We are following its implications all the way to their edge. This question also touches on memory and possibility. Human memory is not a perfect recording of the past. It is a reconstruction shaped by emotion and interpretation. Our imaginations constantly create alternate scenarios, replaying events with small changes to see how things could have unfolded differently. When you wonder what might have happened if you had spoken differently, moved differently, or chosen differently, your mind is exploring parallel possibilities internally. Modern neuroscience shows that when we imagine an unrealized outcome, our brains activate many of the same regions used when remembering a real event. In this sense, the brain naturally generates its own internal multiverse of hypothetical selves. But the deeper scientific question is whether these possibilities exist only in the mind, or whether they exist physically. If space and time extend into directions we cannot perceive, or if quantum events truly branch reality, then these alternate versions of you might not be confined to imagination alone. They could be part of the structure of existence itself, woven into the fabric of reality, the same way stars, galaxies, and particles are. The question of another you ultimately invites us to confront the scale of the universe. We often think of ourselves as isolated beings, living a single life on a small planet. But the more we learn about physics, the more we see that our existence might be just one thread in a much larger tapestry. The possibility of other versions of you isn't meant to replace your identity or diminish your life. Instead, it expands the context in which your life unfolds, suggesting that reality may be far more intricate and far more layered than our senses alone can reveal. In the next part, we turn to history to see how ancient cultures imagined multiple worlds long before science began to explore them, and how the human intuition for other realms eventually evolved into one of the most profound scientific questions of our time. For thousands of years before science existed as we know it, human beings tried to make sense of the world through stories. When people looked at the sky, felt the movement of the seasons, or experienced strange moments of intuition, they often believed there were other realms beyond the ordinary. These weren't scientific theories, but they were remarkably imaginative attempts to describe a layered reality, full of hidden worlds and unseen forces. In ancient India, philosophical traditions described endless cycles of creation and destruction, where universes were born and dissolved again and again. These weren't isolated worlds, but entire cosmic systems, each with its own structure and timeline. In early Greek thought, philosophers like Anaximander and Democritus speculated that there might be countless worlds made of different combinations of atoms, each forming its own heavens and earths. Norse mythology imagined the cosmos as a great tree with many interconnected realms, each one distinct, yet part of the same larger structure. And in many indigenous cultures, there were beliefs in spirit realms layered alongside the physical one, places that could be reached through dreams or altered states of consciousness. Although these ancient ideas weren't based on experiments or mathematics, they show something important. Humans have always sensed that reality might be more than what we see. Long before quantum mechanics or cosmic inflation, people felt intuitively that the world might contain other versions of existence, other places where events unfold differently. Their stories weren't scientific descriptions, but they were early expressions of the same curiosity that drives modern physics. As civilizations grew more complex, so did their questions. The ancient world had no telescopes, no particle accelerators, and no equations to measure the forces of nature. But people were already wrestling with concepts like infinity, multiple realms, and alternate possibilities. These early metaphors laid the emotional groundwork for ideas that scientists would later explore with precision. When we look back, it becomes clear that the human mind has always been drawn toward the mystery of hidden worlds. It wasn't until the 20th century when physicists began studying the behavior of atoms and light, that the idea of multiple universes gained scientific footing. Experiments showed that particles acted in ways that defied ordinary logic, suggesting that reality at its smallest scales might contain many overlapping possibilities. What began as myth and philosophy gradually transformed into scientific theory grounded in mathematics and evidence rather than story alone. The shift from myth to physics wasn't a rejection of imagination, it was an expansion of it. Science took the ancient intuition that reality has layers and began exploring those layers with new tools. Instead of gods or spirits, scientists found equations and probabilities. Instead of symbolic worlds, they found quantum states and cosmic expansion. But the feeling is the same, a sense that we live inside something vast and interconnected, something that stretches far beyond our everyday experience. As you let these ideas settle, you might notice how natural it feels to imagine beyond the boundaries of the familiar. Human beings have always done this. It is part of who we are. And now, with the discoveries of modern science, we can follow that instinct further than ever before. In a moment, we'll gently step from myth into the foundations of quantum physics itself, the place where the scientific story of parallel universes truly begins, and where the fabric of reality reveals just how many possibilities it can hold. When scientists first began to explore the world at unimaginably small scales, they expected to find simple building blocks, tiny particles acting like miniature versions of the objects we see around us. But the moment they looked closely enough, the universe behaved in ways no one expected. Light sometimes acted like a particle, and other times like a wave. Electrons could exist in multiple states at the same time, and systems behaved unpredictably unless they were observed. This strange new territory became known as quantum mechanics, and it quickly became clear that the familiar rules of everyday life do not apply in the quantum world. One of the first surprises came from experiments with light. When scientists passed light through two narrow slits and measured the result on a screen, they found an interference pattern, a sign that light was behaving like a wave, spreading across both slits at once. But when detectors were added to check which slit the light went through, the pattern disappeared, and the light behaved like individual particles. It was as if the act of observing forced the system to choose just one outcome. Even more mysterious was the behavior of electrons inside atoms. Instead of orbiting the nucleus like tiny planets, electrons occupy probability clouds, regions where they are likely to be found, but not guaranteed. Before measurement, they exist as a superposition, a combination of all possible states. Only when observed do they appear in one definite place. These discoveries challenged our most basic assumptions about reality. In classical physics, objects have definite positions, speeds, and properties whether we observe them or not. But quantum mechanics showed that possibilities exist simultaneously until a measurement collapses them into a single outcome. This collapse is not just a mathematical trick, it is part of how the universe behaves. And the more scientists studied it, the more it seemed that the world is built from probabilities rather than certainties. This is the beginning of the idea that there might be other versions of reality. If particles can exist in multiple states at once, then perhaps outcomes can branch into multiple versions of events. When a quantum system is measured, we see one result, but the mathematics suggests that other results still exist somewhere within the structure of the wave function. Some interpretations treat this as nothing more than a mathematical tool, but others take it literally. Quantum mechanics also revealed phenomena like entanglement, where two particles become linked in such a way that measuring one instantly affects the state of the other, even across great distances. Einstein famously called this spooky action at a distance, but experiments have repeatedly confirmed that entanglement is real. It suggests that information in the universe can be connected through hidden layers that do not fit within classical notions of space or time. As scientists uncovered more details, they found that the quantum world is not just strange, but profoundly rich. Superposition, uncertainty, wave functions, and entanglement all point to a universe that contains far more possibilities than we can observe at once. And these ideas set the stage for theories that propose not just different states within a single universe, but different universes altogether, each one representing a separate branch of quantum possibility. Quantum mechanics is not merely the beginning of modern physics, it is the beginning of understanding that reality itself might be fundamentally plural. What looks solid and singular at our scale may be, at its foundations, a dynamic web of overlapping potential worlds. And now that we've opened this door into the quantum realm, we can move deeper into one of the most influential and daring ideas to emerge from it. In the next part, we will explore the many worlds interpretation, a theory that takes quantum possibilities seriously and imagines a universe where every outcome becomes real in its own branch of existence. As quantum mechanics grew more successful at explaining the behavior of particles, scientists faced a strange contradiction. The equations showed that systems existed in many possible states at once, but every time an observation was made, we saw only one outcome. Physicists began asking what exactly causes the wave of possibilities to collapse into a single reality. Some believed that measurement itself forced the collapse, while others argued that consciousness played a role. But in the mid-20th century, a young physicist named Hugh Everett proposed a radical solution. What if the wave function never collapses at all? What if every possible outcome happens, each in its own branch of reality? Everett called this the relative state formulation, but today it is known as the many worlds interpretation. According to this view, the universe is constantly branching. Whenever a quantum event with multiple possible outcomes occurs, reality splits, creating separate versions of the universe where each outcome is realized. These universes do not interfere with each other, and we experience only the branch that corresponds to our own timeline. But the others continue to exist, evolving just as ours does, containing versions of us shaped by different choices and circumstances. At first glance, this idea seems extravagant, an endless multiplication of universes, each containing its own stars, planets, histories, and conscious beings. But Everett's theory has a simplicity that appealed to many physicists. It removes the need for wave function collapse by treating the equations of quantum mechanics as completely literal. Instead of forcing the universe into a single outcome, it allows the full structure of the wave function to unfold. There is no special role for measurement or observers. The universe simply follows its mathematical rules continuously, without interruption. One of the surprising implications of this view is that quantum uncertainty is not a sign of randomness, but a sign of branching. When we perform an experiment, it does not give one result or another randomly. Instead, new branches form, and in each branch, an observer sees one result. The experience of randomness comes from the fact that we exist within only one branch at a time, unable to perceive the others. Many scientists initially dismissed Everett's idea, thinking it was too speculative or too philosophical. But over time, as experiments became more precise and quantum behavior became harder to interpret through traditional lenses, the many worlds interpretation gained respect. Today, it is one of the major interpretations of quantum mechanics, not because it has been proven, but because it offers a consistent and elegant explanation for the strange behavior of the quantum world. In this interpretation, the universe is an ever-expanding tree of possibilities, each branch containing its own version of reality. Every decision, every quantum event, every interaction that could unfold in more than one way becomes a point of divergence. The idea does not say that every imaginable world exists, but rather that every quantum-consistent outcome does. This includes countless small variations, an atom decaying in one branch but not another, a photon traveling left instead of right, or even larger differences influenced by chains of events stretching across time. It is natural to wonder whether these branches could ever interact, or whether we could cross from one to another. According to Everett's view, the branches are separate because their quantum states no longer overlap. Once they diverge, they evolve independently. While the mathematics suggests that interference between branches is theoretically possible, in practice, it is far beyond our technological reach. The sheer scale of these branches makes communication or travel between them effectively impossible with our current understanding. Still, the idea reshapes how we think about existence. It suggests that the universe is not a single narrative, but a vast collection of narratives, all unfolding simultaneously. It raises profound questions about identity, choice, and destiny. If every decision you could have made exists in some branch, then what does it mean to choose? If countless versions of you exist, what makes this version unique? These questions lead us deeper into the philosophical side of the multiverse. But before we explore those ideas, it helps to look at a famous thought experiment that demonstrates exactly how quantum possibilities create paradoxes and how the many worlds interpretation addresses them. In the next part, we turn to Schrödinger's cat, a strange and iconic scenario that reveals why scientists were forced to rethink the nature of reality itself. One of the most famous thought experiments in the history of science was never meant to explain quantum mechanics. It was meant to expose how absurd quantum rules seem when applied to everyday life. In 1935, physicist Erwin Schrödinger described a scenario involving a sealed box, a small amount of radioactive material, a detector, a vial of poison, and a cat. According to quantum theory, the radioactive particle could decay or not decay, and until it is observed, it exists in a superposition of both states. Schrödinger extended this logic to the macroscopic world, suggesting that if the particle is in two states at once, then so is the entire system. In other words, the cat inside the box would be both alive and dead at the same time, at least until someone opens the box and observes the outcome. this idea was not meant to be taken literally. Schrödinger intended it as a critique of quantum theory, but instead of weakening the theory, his paradox exposed how deeply strange the nature of reality becomes at microscopic scales. If quantum mechanics is correct, and countless experiments confirm that it is, then the boundary between the quantum world and the classical world is not as clear as we once believed. Somewhere between atoms and living beings, probabilities must collapse into definite outcomes. But where and why? For decades, scientists debated how to interpret this paradox. Some argued that the act of measurement forces a collapse of the wave function. Others said that consciousness plays a role, suggesting that an observer's awareness determines the outcome. Still others believed that the wave function is only a mathematical tool, not a physical structure. But none of these explanations resolved the deeper question of why the universe behaves differently at different scales. The many worlds interpretation offers a different explanation. Instead of collapsing the wave function, it allows both outcomes to occur in separate branches of reality. In one branch, the particle decays, the poison is released, and the cat dies. In another branch, the particle does not decay, the poison is not released, and the cat lives. When the box is opened, the observer becomes part of the branching process. In one version of the universe, the observer finds the cat alive. In another version, the observer finds the cat dead. Each version of the observer experiences only one outcome, but both outcomes are equally real within the structure of the multiverse. In this view, Schrödinger's cat is not both alive and dead in the same universe. Instead, the universe itself splits. The paradox dissolves because there is no need for the wave function to collapse. Reality simply follows both paths, each in its own branch. This explanation avoids the need for consciousness to affect physical systems and treats measurement as just another physical interaction. The universe branches naturally, creating multiple versions of events every time quantum uncertainty is involved. Some people object to the idea of a constantly branching universe, finding it wasteful or extravagant. But from the perspective of physics, it is no more extravagant than assuming the wave function collapses in a mysterious or undefined way. Many worlds preserves the mathematical structure of quantum theory without adding extra rules or assumptions. It is a bold idea, but it fits the strange behavior of the quantum world remarkably well. The Schrödinger's cat paradox also highlights how limited our intuition can be. We are used to thinking in binary terms. A cat must be alive or dead, a particle must go left or right, an event must happen or not happen. But quantum systems do not follow this logic. They exist in fluid, overlapping states until interactions force them into more defined configurations. When we apply this logic to larger systems, it challenges our understanding of reality itself. As the idea of parallel outcomes grew, scientists began looking for ways to test these ideas using large-scale cosmic phenomena. What if universes do not only branch at the quantum level, but also form independently on enormous scales? In the next part, we move from tiny particles to the vast structure of the cosmos, exploring the possibility that our universe might be just one bubble among many in a far larger cosmic landscape. As scientists shifted their attention from the smallest scales of quantum mechanics to the largest scales of the cosmos, They discovered that the universe itself carries clues that point toward the possibility of multiple realities. When we look out into space with powerful telescopes, we see billions of galaxies, each containing hundreds of billions of stars. But beyond that immense richness lies something even more mysterious. The structure of the universe, the way matter is spread out, and the way space expands all suggest that our universe may be only one region in a far greater cosmic landscape. The idea begins with the question of why the universe looks the way it does. When we observe cosmic background radiation, the faint afterglow of the Big Bang, we find that the temperature is almost perfectly uniform in every direction. This uniformity is surprising because distant parts of the universe are so far apart that they should never have had time to influence each other. Yet they show the same conditions, as if they somehow communicated faster than the speed of light, or shared a common origin more connected than current physics allows. To explain this, physicists developed the theory of cosmic inflation. According to this idea, the universe expanded tremendously fast in a tiny fraction of a second after the Big Bang. Space itself stretched so rapidly that small fluctuations were smoothed out, creating the uniformity we observe today. But inflation has another consequence. If inflation happened once, it might happen repeatedly. In some regions, inflation may end, allowing stars and galaxies to form. In other regions, inflation may continue, causing those regions to expand and separate from each other permanently. The result is a vast cosmic landscape made up of many distinct regions, each one essentially a separate universe with its own laws, structures, and histories. In this picture, our universe is like one bubble in a frothy ocean of expanding space-time. These bubbles may vary in size, shape, composition, and physical laws. Some might contain conditions suitable for stars and life, while others could be simple, empty, or chaotic. These bubble universes are not connected by space in the way we understand it. They drift apart faster than light can travel between them, making communication or travel impossible with any physics we currently know. But their existence is a natural consequence of inflationary theory, not an added assumption. This cosmic landscape expands the multiverse idea beyond quantum branching. It suggests that even the initial conditions of our universe, its density, temperature, and physical constants, may not be unique. In one bubble, gravity might be slightly stronger. In another, atoms might form differently. In yet another, stars might burn brighter or fade faster. These differences could create entirely distinct cosmic histories, shaping unfamiliar structures we can barely imagine. One compelling question arises. If countless bubble universes exist, why do we find ourselves in this one? Some scientists propose that only universes with the right conditions for complexity and life can produce observers capable of asking such questions. This idea is known as anthropic reasoning. It doesn't explain why the multiverse exists, but helps us understand why we observe the particular universe we inhabit. The cosmic landscape suggests that reality might not be a single, precisely tuned creation. Instead, it could be an immense and varied structure, full of regions where physics takes different forms. Our universe is simply one of those regions, shaped by a particular set of laws that allow stars to shine and life to emerge. As we let this idea settle, it becomes clear that the multiverse is not just a quantum curiosity, but a possibility woven into the fabric of space-time itself. And this leads naturally to another question. If there are extra dimensions beyond the ones we can see, could they also harbor worlds parallel to ours? In the next part, we step into the realm of string theory, where the universe is built from vibrating strands of energy, and hidden dimensions may hold entirely new layers of reality. Modern physics often pushes us to reconsider our most basic assumptions, but few ideas challenge our intuition as deeply as string theory. In our everyday experience, the world is built from objects that appear solid and stable. Even when we learn that matter is composed of atoms and atoms of smaller particles, we still imagine these particles as tiny dots or spheres. But string theory proposes something radically different, that the fundamental components of the universe are not particles at all, but tiny vibrating strings of energy. These strings are unimaginably small, far beyond the reach of current instruments. Yet their vibrations determine the properties of everything we observe. A particle of light, an electron, or a quark would simply be different patterns of vibration, like musical notes produced by the same instrument. One striking aspect of string theory is that it requires more than the 3 dimensions of space we experience. According to the mathematics, these strings can only vibrate consistently if the universe contains additional spatial dimensions, often 10 or even 11 in total. These extra dimensions are not wide and open like the ones we move through. Instead, they are curled up into complex shapes at scales far smaller than an atom. We do not see them because they are compactified, hidden within the fabric of spacetime. Yet, even though they are hidden, they influence the behavior of particles, forces, and the structure of physical laws. The existence of extra dimensions raises a profound possibility. If dimensions beyond the ones we perceive exist, then they could allow entirely different configurations of spacetime. In some versions of string theory, the universe resembles a vast, higher dimensional space where our own universe is just one brain or membrane floating within it. Other brains might exist parallel to ours, each one potentially hosting its own universe with its own particles, forces, and forms of matter. These other brains would be separate from ours, yet close in higher dimensional space. We might never interact with them directly, but their existence would follow naturally from the underlying geometry of the theory. Some physicists have even proposed that gravity might be weaker than other forces because it spreads through extra dimensions. If this is true, then gravity could leak from one brain to another, leaving faint signatures in our universe. The idea that multiple brains float alongside each other in a higher dimensional space opens the door to the possibility of parallel universes that are not the result of quantum branching or cosmic inflation, but are instead structural features of the universe's deeper architecture. String theory also predicts objects known as string vacua, different stable ways that extra dimensions can be shaped. Each shape leads to different physical properties. In one configuration, the universe might contain familiar forces and particles. In another, physics might behave differently, producing a universe with unfamiliar rules. Because the number of possible configurations is enormous, some estimates suggest on the order of 10 to the power 500. The theory implies a vast landscape of potential universes, each one emerging from a different arrangement of extra dimensions. While much of string theory remains untested, its mathematical consistency makes it a powerful framework for exploring the fundamental nature of reality. It unites the forces of nature under one theoretical umbrella and offers a way to think about why the universe has the laws it does. Instead of being uniquely determined, those laws may be the result of which configuration of extra dimensions we happen to inhabit. As you let these ideas settle, you might sense how deeply interconnected the layers of reality could be. The dimensions we see are only part of the full structure. Hidden spaces might lie all around us, not distant, but curled up so tightly that they go unnoticed, yet still shaping every particle and every interaction in our world. And now that we've explored the possibility of extra dimensions and parallel brains, we can return to the cosmic scale to consider how entire universes might form within a larger inflating space. In the next part, we'll look at bubble universes and cosmic inflation, and how the early moments of existence may have given rise to countless separate realms. When scientists trace our universe back to its earliest moments, they encounter a period of extraordinary transformation known as cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe expanded at an astonishing rate, growing from smaller than an atom to larger than a galaxy in an instant. This expansion wasn't like an explosion moving outward into empty space. It was space itself stretching at speeds far faster than light could travel. The idea of inflation was proposed to solve several puzzles about the early universe, such as why distant regions look so similar despite never having been in contact. But inflation didn't just solve existing problems. It opened the door to an entirely new worldview. If reality branches with every choice, what does that say about the observer who watches it unfold? In the strange world of quantum mechanics, observation plays a mysterious role. Experiments have shown that particles don't seem to take on definite properties until they're measured. Before observation, they exist as a range of possibilities, a cloud of potential states. Once observed, they appear to choose a single outcome. But what exactly does that mean? Does consciousness itself affect reality? For decades, physicists have debated whether the observer is an active participant in shaping the universe or just a passive witness. The bubble we inhabit cooled and expanded into a structure where atoms, molecules, stars, and planets could form. But elsewhere, beyond the reach of any telescope, other bubbles may be forming right now. Some may be similar to ours. Others may be radically different. The key idea is that inflation creates a constantly growing space-time where isolated pockets stop inflating and become universes like ours, while the larger background continues to expand forever. These bubble universes are separated by regions of space that grow so rapidly that no signal, no matter how fast, can ever travel from one bubble to another. This makes them effectively unreachable. Even if another universe were only a microscopic distance away, in some abstract, higher dimensional sense, the inflationary expansion between the bubbles prevents any interaction. Each bubble becomes its own cosmos, with its own timeline and its own physical reality. The separation between bubbles also allows different physical constants to emerge. In our universe, the strength of gravity, the mass of the electron, and the speed of light are precise values that allow complex structures to form. But in another bubble, those values might differ slightly, leading to universes where stars burn differently, matter behaves differently, or complexity cannot arise at all. The inflationary multiverse thus provides a potential explanation for why our universe seems so finely tuned for life. It may not be the only configuration. It is simply one that permits observers to exist. Scientists have searched for evidence of other bubble universes, but the task is extraordinarily difficult. One possibility is that if two bubbles collided early in their formation, the collision might leave an imprint in the cosmic microwave background, the faint radiation left over from the Big Bang. Researchers have analyzed this radiation in search of circular patterns or distortions that might signal such a collision. While a few intriguing hints have appeared in data, none have been confirmed. Despite the lack of direct evidence, eternal inflation remains one of the most well-supported ideas in cosmology. It arises naturally from equations that describe the early universe and predicts a multiverse without requiring additional assumptions. For many physicists, it is a compelling bridge between the quantum world and the cosmic world, linking microscopic fluctuations to the vast structure of space-time. As the idea of bubble universes took shape, scientists began to explore another question. If quantum mechanics allows particles to be entangled across great distances, could there be any form of connection, however subtle, between separate universes? In the next part, we step into the strange world of quantum entanglement and consider what it might tell us about information, reality, and the possibility of hidden connections across different branches of existence. One of the most surprising discoveries in modern physics is the phenomenon known as quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they may be. This connection is not a form of communication in the ordinary sense. It does not transmit signals or energy faster than light. Instead, it reveals something deeper about the structure of reality. The universe contains relationships that do not fit within the familiar limits of space and time. Entanglement was first viewed with suspicion. Einstein, who disliked the idea, called it spooky action at a distance, believing it must indicate that quantum mechanics was incomplete. But over the past decades, countless experiments have confirmed that entanglement is real. When two particles are created together or interact in certain ways, their quantum states become inseparable. Even if they move to opposite sides of the universe, the measurement of one will correlate with the state of the other instantly. The effect cannot be used to send messages, but the correlation is undeniable. Quantum entanglement challenges the classical view that systems are separate and independent. Instead, it suggests that the universe is fundamentally relational. Particles do not carry isolated properties. They are part of a larger quantum state that encompasses both of them. This interconnectedness raises profound questions about the nature of information. If entangled particles share a quantum state, then information about that state is not located in either particle individually, but in the relationship between them. Information becomes a property of the system as a whole, not contained within a single point in space. Some physicists have proposed that entanglement is not just a curiosity of small particles, but a foundational feature of reality. According to certain theories, the geometry of space-time itself might emerge from patterns of entanglement. In this view, space is not a static backdrop, but a network of relationships woven from the correlations between quantum states. If true, then entanglement could provide a link between the quantum world and the structure of the universe on large scales. The question naturally arises: if particles in our universe can remain connected across vast distances through entanglement, could there be forms of connection between different universes? This idea remains highly speculative, but it invites fascinating possibilities. If the multiverse consists of separate branches or bubble universes, entanglement might exist within each branch, but not between them. However, some theories suggest that all branches might remain part of a larger, unified quantum structure. In this case, entanglement could reflect deeper relationships that span across different layers of reality. At the very least, entanglement shows that reality is not as isolated as it appears. The classical notion of separate, independent objects breaks down in the quantum realm. What looks like distance or separation may be only part of the picture. At the very least, entanglement shows that reality is not as isolated as it appears. The true nature of the universe might include hidden networks of information that operate beyond our direct perception. These networks could shape how matter forms, how energy behaves, and how the universe evolves. Entanglement also raises questions about observation and knowledge. When two entangled particles are measured, the act of observation does not cause information to travel between them. Instead, the measurement reveals correlations that were already present. This means that the universe contains patterns that exist independently of any observer. The act of observing does not create reality, but uncovers relationships that were always there, waiting to be revealed. The more scientists study entanglement, the more it seems to point toward a universe that is fundamentally interconnected, where information is not limited by space, but woven into the fabric of existence itself. And while entanglement does not currently offer a mechanism for communication across universes, it expands our sense of what might be possible in a reality that contains multiple layers, dimensions, or branches. With these ideas in mind, scientists began to consider whether our universe itself could be a kind of information structure, perhaps even a simulated one. In the next part, we'll explore the concept of simulated realities and what it means for our understanding of identity, consciousness, and parallel universes. As scientists and philosophers continued exploring the boundaries of what reality could be, a new possibility entered the conversation, one that didn't come from ancient stories or from the structure of space-time, but from the rise of technology itself. This is the idea that our universe might be a simulation, a vast computational structure running on some kind of underlying substrate. At first, the concept sounds like science fiction, but the more we learn about physics, information, and consciousness, the more seriously some researchers consider it. The roots of the simulation idea go back to questions about whether the universe behaves like a mathematical system. As physicists developed theories about quantum mechanics and general relativity, they noticed that the laws governing the universe could be expressed with remarkable precision using mathematical equations. Some began to wonder whether the universe wasn't just described by mathematics, but built from it. In this view, the physical world might be the emergent result of deeper rules operating beneath the surface, rules that resemble the logic of computation. One of the reasons the simulation hypothesis gained attention is that the universe appears to have limits that resemble those in digital systems. Space, according to some theories of quantum gravity, might not be infinitely divisible. Instead, it could be quantized, meaning it comes in discrete units. Information itself appears to have limits as well. The amount of information that can be contained within a region of space, such as inside a black hole, seems to be finite. These observations hint that the universe might be built from fundamental units of information rather than continuous fields. Another argument comes from the rapid progress of human technology. If a civilization becomes advanced enough, it might develop the ability to simulate entire universes with conscious beings inside them. If this is possible, then the number of simulated universes could vastly outnumber the number of original physical universes. From a purely statistical perspective, it would then be more likely that we are inside one of the simulations rather than the original. This is part of the argument proposed by philosopher Nick Bostrom, who suggested that unless advanced civilizations lose interest in creating simulations, the odds favor the idea that we are living inside one. The simulation hypothesis also raises questions about consciousness. If consciousness arises from information processing, and if information can be processed in both biological and artificial systems, then there may be nothing inherently impossible about conscious beings existing inside a simulated environment. In this perspective, consciousness does not require a specific physical substance like neurons. It requires patterns, relationships, and the ability to process information. A simulation could, in theory, create these conditions. Of course, the idea also faces significant challenges. There is no direct evidence that we live in a simulation, and the hypothesis is difficult to test. Some scientists look for possible hints, such as unexpected limits on particle energies or anomalies in cosmic radiation. Others argue that if the simulation is perfect, we would never detect its boundaries. The difficulty of finding evidence makes the hypothesis both intriguing and elusive. The simulation idea intersects with the multiverse concept in interesting ways. If advanced civilizations can simulate universes, then simulated universes become a new category of parallel realities. They might contain their own branching timelines, their own versions of observers, and their own structures of space-time. A simulated universe might even simulate others. The layers could extend outward or inward, creating a hierarchy of realities. In this framework, the boundaries between physical and simulated universes become blurred. Whether or not we live in a simulation, the idea encourages us to think differently about existence. It shifts the focus from what the universe is made of to what rules it follows. The simulation hypothesis does not diminish the importance of our experiences. If anything, it underscores their complexity. A simulated consciousness is still a consciousness. A simulated life is still a life. Meaning does not vanish simply because of the medium in which it is encoded. If the universe is a simulation, it suggests that the structure of reality is built from information. And even if it is not simulated, the way matter and energy behave still points toward information as a fundamental component of existence. In every interpretation, from quantum mechanics to string theory to cosmology, information plays a central role. This brings us naturally to the next question. If reality contains so many possible paths, could the mind sometimes sense them? Could experiences like déjà vu reflect alternate possibilities our brains can faintly detect? In the next part, we explore déjà vu, alternate paths, and the strange relationship between the human mind and the concept of parallel timelines. Déjà vu is one of the most curious and unsettling experiences a person can have. You walk into a place you've never been, hear a sentence spoken for the first time, or watch an event unfold, and suddenly, for a brief moment, you feel as if you've lived it before. The sensation is fleeting, strange, and often difficult to describe. It can feel like memory, but not quite. It can feel like recognition, but without a source. And it has led many people to wonder whether déjà vu could be a glimpse of an alternate path, a moment where the boundaries between different possible versions of reality briefly overlap. From a scientific perspective, déjà vu is usually explained as a miscommunication in the brain's memory systems. The hippocampus, which handles the formation of new memories, can momentarily misfire, causing the brain to interpret a present experience as something retrieved from the past. This is one of the most grounded explanations, supported by neurological studies showing that déjà vu often arises when signals between regions responsible for memory formation and recognition are slightly out of sync. But the phenomenon remains mysterious. Even with neurological explanations, scientists acknowledge that déjà vu feels uniquely powerful. It doesn't resemble typical memory errors or illusions. Instead, it feels like a brief window into something that is both familiar and unknown. This emotional component leads some researchers to explore whether déjà vu might be linked to the brain's ability to simulate and predict future events. The human brain constantly models possible scenarios, anticipating outcomes milliseconds or even seconds before they occur. A mismatch between these predictions and the unfolding moment might create the sensation of remembering something that is happening for the first time. The connection between déjà vu and alternate paths arises from the idea that the brain holds multiple possible futures and multiple reconstructions of the past. When we imagine different outcomes, what might have happened, what could happen, what almost happened, the brain generates internal branches of possibility. These imagined branches are not literally parallel universes, but they reflect the brain's ability to process multiple timelines simultaneously. In rare moments, these internal simulations might align closely with real experiences, giving rise to the powerful feeling that the moment has already occurred. For those who embrace multiverse theories, déjà vu offers a poetic connection to the idea of alternate selves. If infinite branches of reality exist, each containing different versions of events, then déjà vu could be interpreted as a momentary resonance between two similar paths. It might be a coincidence of structure where your brain in this universe encounters a situation that strongly resembles a moment experienced by another version of you in a nearly identical branch. While there is no scientific evidence to support this interpretation, The idea resonates with the emotional quality of déjà vu. It feels like a reminder that your life could have unfolded differently and that many possibilities lie just beyond your awareness. What makes déjà vu compelling is not whether it is a literal glimpse into another universe, but how it reflects the mind's relationship with possibility. Humans are storytellers by nature. We build narratives, imagine alternatives, and constantly create meaning out of the events we experience. Déjà vu reminds us that memory and imagination are deeply interconnected. Our sense of time, identity, and continuity is built from fragile processes that the brain performs automatically. When those processes misalign, even briefly, we become aware of how thin the boundary between past and present really is. The alternate paths we imagine, roads not taken, decisions not made, shape our identity just as the choices we actually make. Déjà vu may simply be a neurological glitch, but it also serves as a symbolic reminder that life is full of unrealized timelines. It invites us to acknowledge the many ways our existence could have diverged and helps us appreciate the singular path we are currently walking. As we move forward, these questions lead naturally to a deeper idea in both physics and philosophy: the role of the observer. If reality contains multiple possibilities, what does it mean for consciousness to experience just one of them? In the next part, we explore how the observer shapes our understanding of the universe and why consciousness may be more deeply connected to reality than we once believed. In classical physics, the observer is a passive presence, someone who looks at the world without altering it. A falling apple follows its path whether or not anyone watches. A star burns billions of miles away, unaffected by human attention. But in quantum mechanics, the role of the observer becomes far more complex. The act of measurement seems to influence the behavior of particles, collapsing a cloud of probabilities into a single outcome. This has led scientists to ask an unsettling question: does observation help shape reality? To understand why the observer plays such an important role, we have to look at how quantum systems before they are measured. A particle does not have a definite position or momentum. Instead, it is described by a wave function, a mathematical expression containing all possible states the particle could occupy. When a measurement is made, the wave function appears to collapse, leaving behind only one outcome. But the exact nature of this collapse has puzzled scientists for nearly a century. Is it a physical process? Is it a change in information? Or does the collapse occur only from the perspective of the observer? Some interpretations of quantum mechanics suggest that observation forces the system into one state. Others argue that the observer is simply gaining information and that nothing physical collapses. But in the many worlds interpretation, the observer becomes part of the branching process. When a measurement is made, the observer and the system become entangled. In one branch of the universe, the observer sees one outcome. In another branch, they see another. Each version of the observer experiences only their own branch, creating the illusion of collapse, even though the wave function continues unchanged. This idea raises profound questions about consciousness. If the observer becomes part of the branching universe, does consciousness itself split? Is each version of the observer equally real? Are we simply following one thread of awareness while countless others diverge into separate timelines? These questions are not easy to answer, but they highlight the mysterious connection between mind and universe. Observation is not just an act of looking. It is an interaction, a participation in the unfolding of events. Some philosophers propose that consciousness is fundamental to reality, playing a role in shaping the structure of the universe. Others argue that consciousness is an emergent property of physical systems, arising from complex interactions in the brain. But regardless of viewpoint, quantum mechanics shows that information and observation are deeply interconnected. Reality is not an independent, static stage. It is a dynamic process in which observers play an active role. This does not mean that our thoughts can control particles or that we can influence other universes. Instead, it means that our experience of reality is tied to the information available to us. The observer's perspective is what defines the branch of the universe we inhabit. The universe might contain many possibilities, but we navigate only the one defined by our chain of observations and memories. This leads to an even deeper question about identity. If the observer is central to the way reality unfolds, what does that mean for the self? If countless versions of an observer exist across different branches, how do we define which one is truly you? Does identity stretch across branches, or is each version a separate individual with its own consciousness? These questions bring us to one of the deepest and most personal parts of the multiverse discussion. In the next part, we will explore the identity paradox and consider what it really means to talk about another you in a universe filled with branching possibilities. In classical physics, the observer is a passive presence, someone who looks at the world without altering it. A falling apple follows its path whether or not anyone watches. A star burns billions of miles away, unaffected by human attention. But in quantum mechanics, the role of the observer becomes far more complex. The act of measurement seems to influence the behavior of particles, collapsing a cloud of probabilities into a single outcome. This has led scientists to ask an unsettling question. Does observation help shape reality? To understand why the observer plays such an important role, we have to look at how quantum systems behave before they are measured. A particle does not have a definite position or momentum. Instead, it is described by a wave function, a mathematical expression containing all possible states the particle could occupy. When a measurement is made, the wave function appears to collapse, leaving behind only one outcome. But the exact nature of this collapse has puzzled scientists for nearly a century. Is it a physical process? Is it a change in information? Or does the collapse occur only from the perspective of the observer? Some interpretations of quantum mechanics suggest that observation forces the system into one state. Others argue that the observer is simply gaining information and that nothing physical collapses. But in the many worlds interpretation, the observer becomes part of the branching process. When a measurement is made, the observer and the system become entangled. In one branch of the universe, the observer sees one outcome. In another branch, they see another. Each version of the observer experiences only their own branch, creating the illusion of collapse, even though the wave function continues unchanged. This idea raises profound questions about consciousness. If the observer becomes part of the branching universe, Does consciousness itself split? Is each version of the observer equally real? Are we simply following one thread of awareness while countless others diverge into separate timelines? These questions are not easy to answer, but they highlight the mysterious connection between mind and universe. Observation is not just an act of looking, it is an interaction, a participation in the unfolding of events. Some philosophers propose that consciousness is fundamental to reality, playing a role in shaping the structure of the universe. Others argue that consciousness is an emergent property of physical systems, arising from complex interactions in the brain. But regardless of viewpoint, quantum mechanics shows that information and observation are deeply interconnected. Reality is not an independent, static stage. It is a dynamic process in which observers play an active role. This does not mean that our thoughts can control particles or that we can influence other universes. Instead, it means that our experience of reality is tied to the information available to us. The observer's perspective is what defines the branch of the universe we inhabit. The universe might contain many possibilities, but we navigate only the one defined by our chain of observations and memories. This leads to an even deeper question about identity. If the observer is central to the way reality unfolds, what does that mean for the self? If countless versions of an observer exist across different branches, how do we define which one is truly you? Does identity stretch across branches, or is each version a separate individual with its own consciousness? These questions bring us to one of the deepest and most personal parts of the multiverse discussion. In the next part, we will explore the identity paradox and consider what it really means to talk about another you in a universe filled with branching possibilities. When we step back and look at everything we've explored, from the mysteries of quantum mechanics to the vastness of the cosmic landscape, a single truth becomes clear. The universe is far stranger, deeper, and more layered than our everyday experience suggests. Whether we consider the branching structure of the quantum world, the bubble universes predicted by cosmic inflation, the hidden dimensions of string theory, or the speculative possibility of simulated realities, we find that our familiar world is only one way reality can unfold. The multiverse is not just a scientific concept. It is a reminder that existence is richer than any one version of events, any one timeline, or any one perspective. And in the center of all this vast possibility stands the observer, you. Not as an abstract idea, but as a conscious mind experiencing a particular thread of reality. Out of all the potential branches, you are living this one. Out of all the versions of you that physics might allow, you are the one who arrived at this moment, carrying your memories, your emotions, your questions, and your sense of wonder. Your awareness gives meaning to this universe because it is through consciousness that reality becomes experience instead of abstraction. The idea of parallel universes can feel overwhelming. It might seem to imply that everything is predetermined or that your choices don't matter, but that is not what the multiverse suggests. Even if every possible outcome exists somewhere, the life you experience is shaped by the choices you make here. Your actions define the path your branch takes. No other version of you walks this exact path, thinks these exact thoughts, or feels what you feel. Your branch is uniquely yours, carried forward by your awareness from one moment to the next. In a sense, the multiverse enriches the meaning of your existence. It shows that reality is vast enough to contain endless possibilities, yet intimate enough to give your individual experience significance. The universe may be full of alternate versions of events, but none of them replace this moment. None of them erase the value of your presence in this reality. You are not lost in an infinite sea. You are the center of your own unfolding timeline. When we consider the idea of multiple realities, it becomes clear that the true mystery is not the universe itself, but consciousness. The fact that you can listen, wonder, imagine, and reflect is extraordinary. It is consciousness that turns the universe into something that can be experienced. And whether there are many universes or one, simulated or physical, expanding or branching, the miracle of awareness remains the same. You are a point of perception inside a vast and intricate cosmos, and through you, the universe becomes self-aware. As you drift deeper into rest, you can let these ideas settle without trying to solve them. There is no need to hold on to every detail. Just let the scale of the universe, the beauty of possibility, and the mystery of consciousness wash over you. You can allow yourself to relax into the thought that existence is larger than any one story, yet gentle enough to include your own. And now, as this journey comes to a close, take a slow breath. Feel your mind becoming quieter, your body softer, the world around you more distant. You have traveled through quantum depths, cosmic expanses, hidden dimensions, and philosophical reflections, all while remaining anchored to the simple act of listening. Whether you fall asleep now or linger in a calm state, this moment belongs to you. Because in a universe filled with infinite realities, the most meaningful one is the reality you are living right now.